Swayam Prabha. Digital India. Educated India.
So, as I said, we are making khichdi. Okay. Just to recap of what is the algorithm that we are using. Okay. So this thing is called. This particular technique we are studying is called k-means plus plus. This was a paper by Arthur and I can never spell Sergey's name. Vasily Vetsky. Yes, 2007. So again, I mean, I kind of find it surprising that such a algorithm that has been well known for such a long time, it took us until 2007 to find these improvements that have actually made it down to practice. Okay, so what are we doing? I mean, the good thing about this algorithm is that we make minimal changes to the Lloyd's algorithm, right? And really, the only change that we make is kind of like the pain point of Lloyd's algorithm, which is what the initialization. Beyond that, it's going to be exactly the same as Lloyd's algorithm. Okay, so and all it gives is a strategy for this initialization. And let's think about why this has. What is the intuition behind this, right? So some of you had come up to me asking about it, right? So what are we doing? As we said that we start with the first center. We choose that. Let's say we choose that uniformly at random, right? And then for the second, when we go to selecting the second center, we take everybody's distance with respect to the first center. Okay. So let's say this gives me d of x1, d of x2, d of x3, and so on. And this is d of x4. Okay. So then, for the next center, so C2 becomes xi with probability d of xi square divided by summation d of xi square. I equal to 1 to however many number of points at this point, n minus 1. Right? So it's this. Okay. So that's fairly easy, right? It's possible to calculate this. By the way, do we know what? Do you guys know what this kind of random variables are called? That if a particular random variable takes value, let's say alpha 1 with probability p1, alpha 2 with probability p2, and alpha k with probability pk, what are these random variables called? Discrete random variables. This is a multinomial distribution. Right? Binomial distribution it takes only values 0, 1, let's say, and here we are saying that the random variable takes values one of k values, namely the value alpha with the corresponding probability pi. So we're defining its density function using these discrete probability values. So this is a discrete random variable, definitely. More specifically, a multinomial distribution. Okay, so then this is how we choose C2. So C2 will be one of these other points. Okay. So now let's imagine what is really going on. What is going on? So to understand, and this is really a key trick, to understand such an algorithm, I find it easier, and this is really universal, that you sort of think about very, very simple cases, right? And what really happens there. So imagine a dumb simple case in which, let's say, we have all the points. Let's say we have this room, right? I mean, this two-dimensional room, and we have the floor of it, and the points are kind of uniformly spread along here, right? So imagine the points. Somebody has very nicely sort of taken time and put points uniformly on every on the sphere, such that basically in any region of this plane, there's, the number of points is proportional to the area of that region. Okay, what happens there after you select the first point? What is likely to be selected as the second point? Closer points, farther points? Closer points? Will closer points be selected or will farther points be selected? So there's a trade-off, right? The interesting thing is that let's look at this trade-off. Let's say that this is the first center. And we are saying that the points are uniformly sort of spread out in this, right? So that means that the next center, so imagine that this is the radius r, right? So, and imagine that this is a very thin circle around the radius, okay? So now, because this is a thin circle around the radius, maybe this radius, the annulus is of size delta r, where delta r is much, much smaller than r, right? So then all the points in this region are what? Are they, let's consider this point and this point, P1 and P2. Is P1 more likely to be chosen or P2 more likely to be chosen? They're equally likely to be chosen. They're equally likely to be chosen, right? Because see, the normalization is the same for everybody. Because it's a normalization, it's the sum of all the dx's. And for P1 and P2, the numerator is basically the same, right? Because it depends on the distance of P1 and P2 from the center, right? So then the number of points in this at a distance r kind of depends on how many r and how many points are there in this annulus, right? So if the points are uniformly chosen, what is the radius of this annulus? What is the area of this annulus? It's kind of like the 2 pi r times delta r, right? It's the DDR of 2 pi r square, right? I mean, we're taking the derivative, basically taking derivative and multiplying by 2 pi r. So that's the number of points in this annulus. Each of them has probability of being chosen that's proportional to, r square by this sum, by whatever sum, right? So then this you can say is the probability of a point being chosen, of the next point being chosen at distance r, right? So this still kind of increases with r, right? Because this increases with r, this is increasing with r. So this entire probability is increasing with r, which means that the probability that the next point will be chosen at a larger distance is much higher than the probability that it will be chosen at a smaller distance, right? Which kind of means that if the points are uniformly chosen, I mean, if the points lie uniformly on the grid, this behaves more like the farthest point, which is kind of like the right thing to do because the points are uniformly. So if you have created a center here, might as well create a center way far off. Okay, so that makes sense. The other way, the other kind of see, this is a very simple sort of case, but it's useful to get our intuition. The other case is something like this: that suppose we have a bunch of points that are very densely in this region. There are a lot of points lying, and there are a small number of clusters here. I mean, small number of outliers here. Maybe there's one or two outliers here, but then there are a lot of outliers in this. There's another bunch of points here. Okay? And now suppose you have chosen the first center to be at the center of this square, this first dominant region. Now what happens? Now you have to look at, now for the second center, now we're asking, okay, will it be chosen, is it more likely to be chosen from here? Is it more likely to be chosen from here? Right? So imagine that these two are the same distance r from the first center. Where is the next point more likely to come from? From this blob or from this set of outliers? So the first center has been chosen here. Where is the next center likely to come from? From this blob or from this outliers? Where most of them are, I mean, imagine that they're both at distance r from the, I mean, let's say all these points are more or less at distance r from this. All these points are more or less at distance r from this. But the number of points here is much more than the number of points here. Number of points in this big circle is much more than the number of points here. In the circular region. Why is that? Because they're more dense here. Therefore, the total probability, while for every point here, the dx alpha by the normalization is the same as another point here, dx alpha by the normalization. So for individual points, this probability is being chosen is the same, but there are just more points here. So therefore, the total probability mass here is much more than the total probability mass for the outlier region. So therefore, the next point will likely be chosen from the circular region, right? So you see that there is this tension of, okay, how many points are there at a particular distance, right? And how far are they, right? And this is the right kind of tension to play upon. So alpha equal to 0, right, kind of looks at only one of them. Okay? It kind of looks at, okay, how many points are there? Because uniformly and random means that more points are out there, means that it's more likely. Alpha equal to infinity looks at only the other side of the tension. It looks at, okay, how far off. But this kind of combines the two sort of tension factors into, and this happens to be the right kind of combination. This alpha equal to 2, and the alpha equal to 2 is no magic. It's a right kind of combination because we're looking at the distance squared. If we were looking at a distance to the power 1, this alpha would change. It would be, as your right guess is, probably 1. Right? Although I'm not entirely sure of that, so you should check that out in the experiments today. Okay, so then this is really the intuition, that it kind of basically tries to say that, okay, I really want to get away from the current set of centers, right? But I don't want to choose, I mean, if there are one or two outliers, I don't want to be choosing them. I mean, if possible, right? So unless, let's say that we have here, but then there are very small outliers that are very far here. Let's say that the very small outliers that are very far apart from the center. Then because this capital R is much more than the small r, if this capital R is much more than the small r, then the probability here is proportional to capital R to the power alpha divided by the normalization factor. So I'm writing Z as a normalization factor, which is the same for everything. And it's possible that this is much more than the total probability here, right? So unless if and this is reasonable, that if the outliers, even if they're small, if they happen to be really, really far apart, right, then it makes sense to actually declare them as their own cluster. But if they're not so far apart and there are not so many of them, then I don't really want to do that. That's basically the intuition, okay? And we'll try to see how have they formalized this? Questions? Any questions? No? Okay. So what is the benefit? Okay. So, and here is a clear benefit. I'm writing this as a theorem, then we'll explain what it means. The algorithm returns a log k approximation. Remember what is k? K is the number of clusters. So what does it mean that it returns a log k approximation? You might not have studied an approximation algorithm before. I've thrown a lot of things at you. This is a randomized algorithm. This is an approximation algorithm. So what is an approximation algorithm? An approximation algorithm is that suppose you have an objective function, right? And the objective function you optimize, and suppose the optimum value is opt, right? And you want to get, and suppose you're trying to sort of minimize this, okay? So then if you cannot minimize it, then suppose you can get to, you have an algorithm that can give you a solution that's within opt over 2. The cost of the solution, the cost of the algorithm, right? Oh, sorry. I should really talk about minimization. So let me erase all ink on the slide. So you have objective function that you are minimizing, and the optimum solution is opt. Now, suppose somebody tells you that, okay, I'm not able to completely minimize it, but I'm giving you a solution that I call the algorithm, and the cost of this algorithm is less than twice opt, right? Let's say you really wanted to get. I'll give you a machine learning example. You really wanted 99% accuracy. You get like 60% accuracy, right? So this is the objective function, optimum objective function. So we call this a two approximation. Right? So what it means is that, okay, I cannot guarantee that I'm giving you the optimal solution, but I can give you which is not much worse than optimal. And this is less than equal to 2 because we are doing minimization, right? If it was doing maximization, then it would have been the other way around. Okay. So for this algorithm, then what are we saying? We are saying that the cost of this k-means plus. And remember, the definition, what is the definition of cost? The definition of cost remains the same, which is the k-means objective, right? Which means that the objective function of this algorithm will be at most some constant times the log k of the cost of the optimal solution, right? Which is quite astounding, right? Because previously, remember what happened in previous Lloyd. In previous Lloyd, we saw examples, right, where we could get to solutions that are arbitrary, that could be much worse with respect to optimal, right? Remember this particular example that we saw, this particular example that we saw, right? If this distance, right, is much smaller with respect to this distance, then the solution that we get is way worse than the optimal, right? So we have and we completely sort of go around that, right? We completely sort of go around that and say that, okay, give me this is like a worst case example. Well, I mean worst case guarantee, which says that give me any input, doesn't matter. Think as hard as you can. Give me any input, right? I'll guarantee that using the k-means algorithm, right, I don't return you a sort of solution that is much worse with respect to optimal, right? And you might say that, okay, log k, what is that? And what are the typical values of k that you take, right? Today we'll deal with MNIST data set which deals with k equal to 10. K equal to 10 log k is very reasonable. However, in certain settings, you might be dealing with k equal to 1000. What is log k? Who knows? This is probably log 2. So 2 to the power 10 is like 1000. So log k is about 10. 10 approximation. Starts getting a little iffy. What happens if k equal to 1 million? If you have 1 million clusters, you typically don't have 1 million clusters. But even if you do, this is a theory bound. What you will see today in the experiments itself is that you get actual guarantees that is way better than this log k approximation, right? In fact, you get guarantees that is very comparable to anything any algorithm. So how do we capture that? We capture that by saying with this kind of guarantees. Right? What this guarantee says is that suppose the data happens to be nicely clusterable. So I'll sort of define what it means. Right? Intuitively, what it means is that the data is such that the data is not like this. See, if the data is like something like this, the straight line, I mean all points on the straight line, basically all points on this continuum, then there is no real cluster structure present, right? Because if you take a single cluster here versus if you take 3 clusters here versus if you take 5 clusters here, I mean, it's not really just clusterable. However, look at this data. There is clearly 2 nice clusters possible, right? So I don't know how to capture that formally, but suppose this is the intuition that if the data happens to be nicely clusterable, right, then in fact your k-means algorithm doesn't just return a log k approximation, it returns a constant factor approximation. This O1 is a constant, which means that this is, let's say this constant is like 3, that your solution is never a factor 3 worse than that of optimal. This is what it means. Is this clear? Any questions here? Is the concept of approximation clear? Right? That the cost of the k-means cost of the solution that we are going to return is never going to be much worse than that of the optimal cost. So think of it this way, right? Even if you don't understand all the value. See, that's the point. I mean, I don't care what the value of the cost is. What we are saying is that for this point set, whatever be the value of the, okay. So first of all, you know what the objective function. So what is this cost function? This cost function is the k-means objective function, right? Which I mean, I should just write it down actually. Let me just write it down. So this is the summation over all x, mean over cx, t of x cx square. This is the cost that we're talking about, right? And I don't care what the value of this cost is. That's the point. The algorithm doesn't know the optimal value of the cost. However, it is guaranteeing you, right, that run this algorithm, whatever be the optimal solution, and the corresponding cost for that, you're not going to be too far off from there. Oh, it's a specific constant. I don't remember what the constant is. Yeah. But again, the point is that these are. I mean, you should look at it from the point of view of not just the constants, but what is it really trying to say, right? Because the actual constant. So the objection was that okay, order 1 it can be 1 million, right? 1 million is order 1, right? And does that mean anything? Likely not for the realistic data sets. But if you think about it, that what do these theorems mean? They really are talking about that if you let n go to, does this depend on n? Does this depend on k? Right? And the actual constant that you put here is likely a function of the analysis you're able to do. Okay? And in practice, you get results that are much, much better than the constant that you derive in the proof. Let's just put it that way. Okay, and I don't remember what the constant derived in the proof is, but I mean we'll look at the theory. I mean practical results in this. Yeah, and so that's does that answer your question?
Log k is the worst case, constant is the best case.
No. So that's again a very good point to sort of interrupt upon. So these two theorems are saying two different things. The first theorem is saying is that doesn't matter how the point set is, right? This algorithm always returns you. So both of these are worst case. I mean, not exactly. No, I mean, let me recorrect it. Okay, so let me rephrase it. So reset to a few seconds. Okay, what the first theorem is saying is that look at the worst case input. Okay, so somebody looks at the algorithm, designs the input for it. You are still going to get a log k approximation. That is the worst case. The other theorem is saying is that okay, the algorithm, I mean, nobody is really designing a worst case input. It may not be best case, but it's not worst case either. It's like that this particular input that we're getting has a nice cluster structure with k clusters. In that case, we get a constant factor approximation. Okay? Any other questions here? Okay. Okay. So let's look at a more precise definition of what is nicely clusterable. Okay, so here is what we say. That suppose we call an algorithm with nicely clusterable with the we call a data set to be nicely clusterable with the parameters k and epsilon. So think of k as the number k and epsilon as something like, I don't know, 0.1. Right? If the following happens, right? So imagine this point set. There are a bunch of points here, then there are a bunch of points here. So in this particular point set, in the squares and the crosses, there is really a difference between using one cluster and using two clusters. Would you agree? That if you use one cluster, right, then you cannot get the objective function to be really low. Whereas if you use two clusters, the objective function suddenly drops. So there is a right number of clusters present, so to say, right? And that's exactly what the definition sort of says. What it says is that there is a small constant epsilon such that using k clusters is much, much smaller than using, the cost of using k clusters is much, much smaller than the cost of using k minus 1 clusters. So think of k equal to 2 here. So the cost of using two clusters here is potentially much, much smaller than the cost of using one cluster. This is when we call the data set to be nicely clusterable. Right? I'm just throwing you this definition. Okay? And under such circumstances, we can say that k-means really shines. It sort of gives you a very, very sort of good approximation, right? But even otherwise, even if somebody is designing the data set to be adversely worse with respect to you, it doesn't do very badly. Epsilon is some small constant, right? That's used in the parameter. So think of it as some small constant less than 1. This is more a technical definition. So, that's because this is also squared. Remember, this is also squared. This is so the distances have been squared in both of them. I think it's more in line to sort of keep the units to be the same. This is epsilon squared. basically. There's no particular reason that this, I mean, I could have defined it with epsilon also. There's no particular reason. Yeah. Okay. Is it clear? Sort of? Okay. Okay. So why does it work? And this is what we have been talking about. And I'll try to frame it a little more, right? So here is the first thing that we say. Here's the first thing that they prove, right? And we won't prove this, right? But here is the intuition. So the intuition is something like this: that suppose the optimum clustering. So there is some optimum clustering, right? Which is that suppose God had told us that, look, this clustering is really the optimum of the k-means objective function. Okay. So now imagine what is happening to the k-means plus plus. So what we claim is that if the first point is chosen from some cluster of the optimum, right? The first point is chosen from some cluster of the optimum, and what we claim is that this cluster, right? That the total cost of this cluster is approximated pretty well because I've already placed a point in the first cluster, right? This is not very hard to show. So it really uses triangle inequality. It's a form of triangle inequality because optimum plays some point here, and it's sort of maybe somewhere here. So therefore, the distance of any point to the optimum center is can be said that it's kind of not very far of the distance of this point to my center and the distance of the center to the optimum. So that's not very hard to show. So the first cluster that my k-means plus plus chooses a point from, that is approximated fairly well, right? Then the second cluster, then now onwards we kind of do it's an induction, right? And it kind of sort of has the same kind of intuition. What it says is that suppose there is some cluster of the optimum in which such that k-means plus plus is choosing multiple points from there, right? So why is it choosing multiple points from there? And so even if you sort of don't understand this completely, it's okay, because this is really dense. I mean, and I'm really kind of giving you a very overview sketch of this proof, right? What it says is that, okay, why is k-means plus plus choosing multiple points from this cluster? So remember that the k-means plus plus objective is the summation dx square by summation dx. So the k-means plus plus sampling probability is this. So if it is choosing multiple points from the same optimum cluster, it kind of means that the total probability of choice from this cluster is fairly large, right? Because if I sort of let's say I'm choosing points, students either from here or from here, and if I happen to be choosing multiple students from this side, which kind of means that I prefer this side more, right? That's exactly what it says. If it chooses multiple points on the cluster, which means that the total sum of the numerator is more or less comparable to the total denominator, because the total probability on this cluster is more. And this kind of says that the other clusters don't contribute too much, basically. And then we can focus on this, on sort of trying to approximate the optimum cost on this cluster itself. This is basically, there's very vague intuition. This is nowhere. But if I try to explain it, that would take up the rest of my 2 hours. Okay. So combining these intuitions, what you can say that you get something like a log k approximation for the very worst case input design. However, if the data is already well separated, then the second case doesn't even arise, right? Then what we always get is kind of like the first case, right? If the data is very well separated, that there are k clusters that are very far away from each other, that the data is nicely clusterable, then the k-means plus plus algorithm kind of always happens to choose one point from each of the optimum clusters, and therefore it approximates optimum clustering fairly well. This is the intuition you can take away. That the k-means plus plus sampling probability is designed so that it sort of places a cluster, places a cluster center wherever the optimum tries to place a cluster center in some sense. Your question.
How does it choose the starting points?
So as I said, that the starting point is chosen uniformly at random. At random. Uniformly at random from all the points. And okay, and then onwards you do this, right? But then what you have to say is that, I mean, and I kind of skipped over this. What you say is that this algorithm works with high probability. Right? And the way you say this is that, okay, I'll run this algorithm 10 times, right? I'll run the entire k-means plus initialization plus k-means 10 times, right? And then I'll look at the objective function for each of these 10. I'll take the minimum of these 10 runs. So if I had, let's say, okay, let me see. If I had a chance half, right, of this k-means plus working in quotes in one of these 10 cases, then if I take the minimum, right, then what is the chance that the k-means plus actually has worked in at least one of these 10 cases? Okay, let me make my question a little more precise, because you guys have done probability. So if the probability that k-means plus gives, let's say, a order 1 approximation is at least half. So what is this probability over? Remember, this probability is over the choice of centers, right? Because the choice of initialization. Because the random variable here are the set of centers that we are choosing. So suppose that the probability that the k-means plus gives order 1 approximation is at least half. Suppose now, what I do is that you run k-means plus 10 times with 10 choices of centers and take one with minimum objective function, right? Then can I say that what is the probability that this minimum of the runs gives order 1 approximation? What is this probability? Simple probability calculation.